Interstellar Boundary Explorer is a NASA satellite that is making a map of the boundary between the Solar System and interstellar space. The mission is part of NASA's Small Explorer program and launched with a Pegasus-XL rocket on October 19, 2008. Results from Ibex have repeatedly shocked the scientific community and overturned old theories. The first shock came when it revealed a narrow ribbon of energetic neutral atom emission. Then it showed shifts over time in this band. Another surprise came when no bow shock was found. The repercussions of overturning the bow shock theory are huge, because decades of research are based on that concept. The design and operation of the mission is being led by the Southwest Research Institute, with the Los Alamos National Laboratory and the Lockheed Martin Advanced Technology Center serving as co-investigator institutions responsible for the Ibex High and Ibex Low sensors respectively. The Orbital Sciences Corporation manufactured the spacecraft bus and was the location for spacecraft environmental testing. The nominal mission baseline duration was 2 years to observe the entire solar system boundary. This was completed by 2011 and its mission was extended to 2013 to continue observations. Ibex is in a sun-oriented spin-stabilized orbit around the Earth. In June 2011, Ibex was shifted to a new, more efficient orbit. It does not come as close to the Moon in the new orbit, and expends less fuel to maintain its position. Payload. The heliospheric boundary of the Solar System is being imaged by measuring the location and magnitude of charge exchange collisions occurring in all directions. This will ultimately yield a map of the termination shock of the solar wind. The satellite's payload consists of two energetic neutral atom images, Ibex High and Ibex Low. Each of these sensors consists of a collimator that limits their fields of view, a conversion surface to convert neutral hydrogen and oxygen into ions, an electrostatic analyzer to suppress ultraviolet light and to select ions of a specific energy range, and a detector to count particles and identify the type of each ion. The Ibex High instrument is recording particle counts in a higher energy band than the Ibex Low does. The scientific payload also includes a combined electronics unit that controls the voltages on the collimator and the ESA, and it reads and records data from the particle detectors of each sensor. Mission parameters. The Ibex satellite, initially launched into a highly elliptical transfer orbit with a low perigee, used a solid-fuel rocket motor as its final boost stage at apogee, in order to raise its perigee greatly and to achieve its desired high-altitude elliptical orbit. Ibex is in a highly eccentric elliptical terrestrial orbit, which ranges from a perigee of about 60,000 kilometers to an apogee of about 290,000 kilometers, that is, about 80% of the distance to the Moon. Its original orbit was about 7,000 by 320,000 kilometers, which has changed primarily due to an intentional adjustment to prolong the spacecraft's useful life. This very high orbit allows the Ibex satellite to move out of the Earth's magnetosphere when making scientific observations. This extreme altitude is critical due to the amount of charged particle interference that would occur while taking measurements within the magnetosphere. When within the magnetosphere of the Earth, the satellite also performs other functions, including telemetry downlinks. Launch. The Ibex satellite was carried into outer space October 19, 2008, by a Pegasus-XL rocket. The Pegasus rocket was released from a Lockheed L-1011 Stargazer airplane that took off from Kwajalein Atoll in the central Pacific Ocean. The airdrop occurred at 17 hours 47 minutes and 23 seconds UTC. By launching from this site, close to the equator, the Pegasus rocket lifted as much as 16 kilograms more mass to orbit than it would have with a launch from the Kennedy Space Center in Florida. The Ibex was mated to its Pegasus-XL rocket at Vandenberg Air Force Base, California, and the combined vehicle was then suspended below the Stargazer mother airplane and flown to Kwajalein, a several hours-long flight. The L-1011 arrived at Kwajalein Atoll on Sunday, October 12, 2008. Orbit adjusted in June 2011. Ibex shifted to a new orbit that raised its perigee to more than 30,000 kilometers. The new orbit avoids taking the spacecraft too close to the Moon, whose gravity can negatively affect Ibex's orbit. Now the spacecraft uses less fuel to maintain a stable orbit, increasing its useful lifespan to more than 40 years. Data collection. Ibex is collecting energetic neutral atom emissions that are traveling through the solar system to Earth that cannot be measured by conventional telescopes. These ENAs are created on the boundary of our solar system by the interactions between solar wind particles and interstellar medium particles. On the average, Ibex high detects about 500 particles per day, and Ibex low, less than 100. By 2012, over 100 scientific papers related to Ibex were published, described by the PI an incredible scientific harvest. Astronomical results. Initial data revealed a previously unpredicted, very narrow ribbon that is 2 to 3 times brighter than anything else in the sky. Initial interpretations suggest that the interstellar environment has far more influence on structuring the heliosphere than anyone previously believed. It is unknown what is creating the inner ribbon. The Sun is currently traveling through the local interstellar cloud, and the heliosphere's size and shape are key factors in determining its shielding power from cosmic rays. Should Ibex detect changes in the shape of the ribbon, that could show how the heliosphere is interacting with the local fluff. It has also observed ENAs from the Earth's magnetosphere. In October 2010, significant changes were detected in the ribbon after 6 months, based on the second set of Ibex observations. It went on to detect neutral atoms from outside the solar system, which were found to differ in composition from the Sun. Ibex discovered the Sun has no bow shock. The speed of the heliosphere in relation to the local cloud is thought to be 23 km per second, instead of previous estimate of 26 km per second. Those speeds equate to 25% less pressure on the Sun's heliosphere than previously thought. The velocity of the LISM relative to the Sun's was previously measured to be 26.3 km per second by Ulysses, whereas Ibex measured it at 23.2 km per second. In July 2013, Ibex results revealed a 4-lobed tail on the Solar System's heliosphere. The spacecraft has also imaged stellar wind bubbles, called astrospheres, around other stars, as well as the tails from these astrospheres. Data transfer rate. Compared to other space observatories, Ibex has a low data transfer rate due to the limited requirements of the mission. Ibex data transfer rates are slow compared with other telescopes due to the nature of the data it collects. Ibex does not need a high-speed connection, since it only has the opportunity to collect up to a few particles per minute. Communication from the satellite to the ground is 20 times slower than a typical home cable modem, and from the ground to the satellite only 2,000 bits per second, which is 250 times slower.